Good morning, student. Today we'll discuss about the root locus. Root locus is the locus of roots of the characteristic equation of the closed loop system, as the specific parameter is usually the open loop gain k, which is varied from the 0 to infinity. And in drawing the root locus plot, we should have the idea about angle and magnitude plot. So this angle and magnitude plot, this is the system is given input, then is the output, and this is open loop transfer function feedback is also there. So the closed loop transfer function of this system is calculated by the output by input. Here it is the output, and all of this is the input, and the closed loop transfer function it is given by the output by input is equal to g of s over 1 plus g of s h of s. This is equation number 1. So the characteristic equation can be written if you equate the denominator of the right hand side of this equation equal to the 0. So that is the characteristic equation. So characteristic equation is this. So this is the 1 plus g of s h of s. If you make equal to 0, then that will be the characteristic equation. And this is g of s h of s is equal to 1. And first we'll check the angle criteria. So angle criteria is generally denoted by the angle of g of s h of s is equal to plus minus 180 degree into 2k plus 1, where k is equal to 0, 1, 2 up to this is the n minus n. So n is the number of open loop poles and n is the number of open loop zeros. Okay, so that is the value of k. Second is the magnitude criteria, means the magnitude of this is equal to 1. Okay, so this is the angle and magnitude criteria. Sometimes the characteristic equation may be written as like this. So characteristic equation is generally written as 1 plus this is open loop gain k, I mean to s plus z1, s plus z2, s plus z3 s plus z1. So this n is nothing but the number of open loop poles. How many number of open loop poles are there? And n is the number of open loop zeros. And this is equal to the 0. And here this gain k is varied from your 0 to the infinity. Okay. So for example, we will consider, suppose this example, we have here the g of s h of s, that is open loop transfer function. It is given k into s plus z1 by s plus p1 into s plus p2, s plus p3 into s plus p4. So let us consider this p2 and p3. These are the complex conjugate poles, and this p1 and this p4. These are real poles. Okay. So z is also real. This is not the complex conjugate zero. Okay. Therefore, the angle can be written like this. So angle of g of s h of s is equal to angle because of this z1, it is called phi1. Angle because of this p1, it is theta1. Angle because of p2, it is theta2. Angle because of p3 is theta3. And angle because of p4 is theta4. For angle zeros, we have to write positive sign, and angle poles we have to write negative sign, because this is in numerator and this is in denominator. That's why we have written like this. So the magnitude, for finding the magnitude of this g of s h of s, which is equal to the 1, for that we have to consider the one test point. So this is a complex S plane. This is complex S plane, that is sigma plus j omega. So we have considered that is a this P1, P4, these are the real poles, and this P2 and P3, these are the complex conjugate poles. So we have written like this, and there is one zero. Zero is shown by the small circles, and the poles are shown by the crosses. Okay, so we have the root locus. We can show like this. So let us consider the trace point S. So for the trace point S, we have to find the distance of all these open loop poles and open loop zeros to this trace point S. So this is the first open loop poles, and the angle, we have to draw the line from the test point S to the P1, test point S to the P2, test point S to the P3, test point S to the P4, and test point S to the Z1. And therefore the angle is counter, where to angle is calculated in counterclockwise direction. So this is a theta 1, this is theta 2, this is theta 3, this is theta 4. And the angle made by the zero is called as the phi 1. Okay. So what is the distance A1, A2, A3, A4, and the angle of the Z1 to test point is B1. So by the taking the help of this open loop transfer function, we can find the magnitude of G of S for this system, which is given by the magnitude of G of S H of S is equal to this open loop gain K into S plus Z1. So S plus Z1, it is having the distance of B1 from the test point. Okay, that is the reasons we have written as B1. Similarly, the pole P1, it is having the distance of A1 from the test point to the pole P1. A2 is the distance of test point to the pole S2. This is pole S3. This is pole S4. Okay, so here this A1, A2, A3, and A4, and also B1, these are the magnitude of the complex S plus P1, S plus P2, S plus P3, S plus P4, and S plus Z1 respectively. So we are interested here to find the magnitude and angle condition. So this is the theory behind the root locus, how to find the angle and the magnitude condition, as well as how to locate the open loop poles and open loop zeros in the S plane by considering one test point. Yes. Okay. So this is the general theory behind the root locus. And the next we'll discuss some examples so that we'll get the idea. Thank you very much for watching this video.